Okay, welcome to another interview for the Zero to ASIC course. And today I'm very happy to be joined by Matt Guthaus. Hi, Matt, how are you doing?
Hi, I'm doing great.
So I think probably a lot of people who have seen you before from the FOSSi Dialup series where you presented OpenRAM. And that's the main thing that I want to talk to you about today. So if you haven't heard of OpenRAM or you don't know what it's for, then I really recommend you check out that FOSSi Dialup talk because it's really good and it covers all the basics. But just as a very brief recap, Matt, could you just tell us what OpenRAM is?
Yeah, OpenRAM, it's what's called a memory compiler. And unfortunately, the word compiler is kind of a misnomer. It's back from the silicon compiler days, so that's why it's called a compiler. But it generates basically the layout and timing and all the sort of models you need for memories. So it's basically an IP generator. And it's written in Python. It uses external tools for like DRC checking and spice simulation and things like that. But then it generates all of the views you need to basically be able to use a memory. Because memory design is a bit different than digital design. It's kind of a hybrid of digital and analog design. So it kind of takes into account all those caveats to, hopefully make, working and reliable memories. So that's basically what it is.
So, and for people new to ASIC design, myself included, one thing that I was surprised to find out was as an FPGA user or even a microcontroller user, you're used to having like these blocks of memory that you can just use. But the way that the OpenLANE tools are at the moment is if you want like a big block of memory or a register file or something like that, you just define your register in Verilog. And then the tools just create a massive amount of flip-flops, which are the biggest standard cells. So they use a huge amount of area. So what OpenRAM is doing is using a very custom Bitcell to store the actual 1 or the 0, which is much, much smaller. But then the trade-off is it requires this kind of analog IP around the edge.
Yeah, exactly. The Bitcell, it's a 6 transistor cell, which is roughly like 1/5 the size of a flip flop. And so even when you add kind of the extra decode logic and stuff, you still get area savings anywhere above a couple hundred flip flops or 100 bits. And so it makes sense to use these whenever you use memories. The one limitation, though, tends to be you have to think about read and write ports. Whereas when you have a bunch of flip flops, you can access any of those flip flops in parallel, right, from different addresses, whatever. Whereas with a memory, you can only access one address at a time. So that's why it's it's a little bit different than a bank of flip flops. So a limitation in terms of usage, but with the area savings, it's a big gain.
So one thing that was quite interesting about what you said was if you ever need more than 100 flip-flops, then it's worth it. And that's something that's interesting about the fact that it's a memory compiler written in Python is it's completely customizable, right? You can ask for any number of flip-flops that you want.
Yeah, that's very
Not
true.
flip-flops, the amount of memory.
Yeah. And that's kind of where OpenRAM differentiates a little. So the idea of a memory compiler is you can tell it what size and configuration you want. OpenRAM is really flexible in that basically we let you make many variants of different features and so on, and some of them may end up not working, so you need to test them. Whereas a lot of the commercial compilers, you'll basically get a compiler from a company and they'll say, okay, these 10 settings work. So you can have 10 different SRAMs, that's all you can do. That's the best case usually. Whereas OpenRAM, we can make thousands of different sizes and varieties right now. And it's with most open source stuff, it's kind of user beware, right? But the advantage of that is you can really, customize it for your particular application. And I think that we're going to have some good success there, especially when we start to get many people verifying it and using it and reporting bugs. This whole crowdsourcing model for that is going to make it much more valuable and stronger, I think, than the competing products. So.
Yeah, if people are interested in the validation, then I'm also doing like a series of talks with Andrew Zonenburg, who's doing some verification on various parts of the OpenRAM tests. So But one thing that I was interested to find was that it takes quite a long time to actually create the memory, doesn't it?
Yeah, there's two different there's a couple different settings that it depends on what you want to do. Actually, creating the layout is fairly quick. It can be a few minutes. The thing that really takes the most time is the characterization of the memory. So actually figuring out what the performance is, and we have a setting where you can use kind of analytical models that estimate it, but basically over all those different sizes and different options, they're not very accurate. They give you some sort of a ballpark. We're working on improving those using some ideas from like machine learning and things like that. And so you can expect some improvements in those kind of analytical models. But to get the most accurate estimates, you basically want to do spice simulation. And we're using memories can get pretty big. We try to prune out basically certain bits that you're not using and just look at kind of the critical path of the memory. But even that can get pretty slow when you start doing performance analysis. Um, we've recently added the capability to use the SICE simulator from Sandia Labs. Eric Kiter and their group has this really great, massively parallel SPICE simulator. And we've seen some big improvements with that. So we've been able to simulate up to the 4K byte memory and shown it successfully working. Now, we're still working on the 8K byte and a 16K byte memory, which we've fabricated without simulating. And so we'll kind of see what goes on there. But yeah, getting something you can use can be quick, but then getting something that's accurate can take longer. And that's one of the big challenges with this project, really, is where to compromise.
Hopefully, we'll get some feedback when we get the results back from the test.
Yeah. And I should comment that you mentioned Andrew Zonenburg. I've kind of said we have three phases of OpenRAM. So we had actually a tape out before MPW1, which is what he's testing. The goal of that was basically functionality. So we wanted a functional memory. It actually relied on commercial tools. So it used commercial tools for verification and stuff with the original Skywater PDK that was not open source. And between there and MPW1, we made the transition to the fully open source tool flow. OpenRAM's always been based. OpenRAM can always work with commercial and open source tools, so we were able to utilize some of that, but we had to basically get up to speed with the open source tools with the Skywater PDK. And so MPW1 was basically open source flow with SRAM. And then MPW2 was basically add lots of different sizes of memories. So you can see with the tape out there, we added 10 different variants of memories, which again, we want functionality on them all, but kind of different capabilities. Then I think next generation is going to basically be focusing on performance. So
cool. Yeah, so that was one of my questions for you was what are the kind of the big changes between when you did the talk for the FOSSi Dialup and for what you've just used for submitting to MPW2?
Yeah, so I mentioned we went from the commercial flow to the open source flow. That was the big change, and that required lots of obviously during MPW1 there was lots of things that were kind of changing and fixing the flow and so on. And so we ran into lots of similar problems. So I worked pretty often and frequently with Tim Edwards. Obviously he's the guru of the entire flow, and so we were working with getting just DRC, LVS, clean layouts, and then addressing some of the other issues with memories. In particular, things like, things like you mentioned the Bitcell, where the Bitcell is 6 transistors, but it actually doesn't follow the same design rules that the digital logic follows. In Skywater terms, the Bitcell follows what's called core memory rules. And because this process was actually made to make SRAMs originally, and from Cypress Semiconductor before it became Skywater. And so they have the core rules are basically what's used to make memories. And some of the spacing and things are basically smaller than what you can do in the user rules. So if you run the DRC check with the user rules, it's like, oh, you have 100 million or 100,000 errors. And so kind of coming up with methodologies of like, how do you verify when the DRC checker can't, distinguish those rules from each other. So we kind of did some of that stuff. even things like, reading in the spice models. Some of the simulators had trouble, just reading in, parsing them and doing all the includes. The scale issue with the transistors. The Skywater DR spice models have this, everything's in microns instead of meters like most spice decks. And so kind of addressing those issues when you're doing simulation and LVS and extraction. So lots of kind of small things, just getting the flow working with the open PDK. That took a lot longer than expected, but it's
What doesn't?
yeah.
It's probably worth mentioning here that you're a professor at a university, right?
Yeah, I'm a professor, and I'm also the associate dean of our graduate program in engineering. So,
And so this is like quite a. How long has it OpenRAM been going for anyway?
it's gone through many iterations. It's been going on since at least about 2013. It started out then as a set of Perl scripts, and I kind of evolved, did a major rewrite into Python like a year or so later. And yeah, there was an original NSF grant that let us get some of the basic functionality. And then really, I've been trying to find its niche. And then when this whole thing happened with Google and Skywater, I met Tim Mansell at a conference, and we talked about it. And it's like, this is a perfect match. This is what we've been looking for. This is what they've been looking for.
Yeah,
And so we
because
kind
you
of run from
need
there.
that. So, like in the bottom left hand corner of the die,
Yeah,
we've got those two 1 kilobyte SRAM blocks that are vital for
yeah,
the Pico RV32. So,
yeah. Because it's interesting. If you talk to designers, they're always frustrated with SRAMs that are available to them and the SRAM compilers. I don't think you can talk to a designer that says, "Oh, I'm okay with the memories." And so, but then you talk to the foundries and kind of the memory people, and they're like, "Oh, we can't do anything different. This is the way it's done. We know that these work. You can't change them." And so, really, we've approached it from kind of a different point of view. We've with OpenRAM, where it's like it's the open source mentality of like, we want people to play with it. We want people to break things and see why it breaks, and then fix it and improve it. And it's it's a different way of thinking about hardware design. And so,
so have you had a lot of your students contribute to it over the years?
yeah, there's been probably like a dozen students, a couple master's projects, a few undergrad projects, even. A number of students have contributed through the years. So
Yeah,
it
it's
started
really
originally
cool.
with one of my students' PhD thesis, where he was doing some of those Perl scripts, and we were doing things for reliability of like ultra low voltage memories. So if you run at kind of sub threshold voltage, um, what is the reliability and so on. And so we generated some arrays and things like that for his thesis. And then it kind of grew out from there.
Okay, so maybe you could talk us through the layout of your application for MPW2.
Yeah. So I mentioned this. The goal of this one was to have more functionality of memories, and basically, we in the previous pre MPW tapeout and MPW1, we had focused basically on a dual port memory, and so one read write port and one read port, and that basically all the five memories on the left of the image are dual port memories. But instead of just having the 1 kilobyte size that we taped out before, we basically have four other variants. One is a 1 kilobyte with an 8-bit data word, and then a 2 kilobyte, 4 kilobyte, 8 kilobyte. And so kind of increasing size. And then the other addition on this one was basically the single port memories, which we had not taped out these before. The the dual port memories basically add two extra transistors to the bit cell, and so it increases the area by probably, I'm ballparking, 10-15%. And so having a single port can be smaller. And so we basically got the single port memories working, and we did or five different sizes for that: 1 kilobyte, 2 kilobyte, 4 kilobyte, 8 kilobyte. And then there's two variants of the 4 kilobyte. One has a bigger, I guess the 4 and 8 have a 64-bit data word instead of a 32-bit data word. So you can see that the functionality was not only number of ports, but then also the sizes and then the size of the data words as well. So that's kind of the variety of memories that we created. And in terms of the design, basically it all fits in the user project space. We did basically all of the SRAMs are instantiated at the top level, and then we do gates at that same top level mixed with the SRAM blocks. And then the gates implement functionality for a couple things. There's basically two test modes. One where you can basically scan in a big register value, and that register value kind of decodes to which SRAM you want to use, what the data you want to write or read, and the address, and then kind of the control bits as well. So you can basically scan in kind of this register, clock it once, and then scan out the result to verify memories. So that's one way of doing verification of this. And then the second way of doing verification is basically using the logic analyzer from the Caravel host processor. And so we use that bus to basically access that same register and basically be able to read and write from any one of the memories at a time. We probably should have added a third method of using the actual wishbone bus as well. We thought about that kind of at the last week or so, but we didn't really want to change the design too much in the last while.
Yeah, it's always a bad idea.
Yeah, and I should mention that this was actually based on a class project with two students. One of them is my graduate student, Jesse Sirmelli-Lowe, and then Amag, who is I don't know how to pronounce his last name, but he's a graduate student of Professor Jose Renaud, and they were taking my VLSI class, which basically everyone was targeting this shuttle run, and so they spent like another 2 weeks after the end of the classes to basically finalize this design and get it out the door. The timeline worked out really well. So
Yeah, it's very cool seeing this. So regarding MPW2, what was the hardest part of getting all of this ready?
so I would say that the hardest part, I thought that going into it, using like getting the OpenLANE flow and stuff going would be a little more straightforward than I thought. But I think it was hard to kind of manage the different versions of OpenLANE as well as the tools in OpenLANE, because with the memories, I was basically submitting patches to things like Magic and NetGen, and and those were changing. So I needed the newest versions of those tools. But then OpenLANE would have older versions, and so I had to basically upgrade the Docker image to have newer versions and so on. So I think tracking versioning was kind of the hardest issue. With the tool flow, with OpenRAM, because with OpenRAM also I have the OpenRAM code and then the what we call the build space, which is basically the cells and the technology stuff for Skywater that configures OpenRAM to do what we need. And so tracking those as well, can get things mixed up. So
Yeah. And there's like a special, like you mentioned, if you just try to run the DRC checker on a design that includes OpenRAM, then you're going to get 100,000 DRC errors.
yeah.
And that was causing a lot of problems right at the end, I noticed on the MPW2 submission date. So
Yeah.
what's the workaround about that? I don't quite understand how that was resolved.
So basically, when we run OpenRAM, we do DRC and LVS and report the results. And when we do DRC, the Bitcell itself basically will not pass DRC checks. And so what we do is we use kind of a methodology that Tim Edwards kind of suggested, where it's called a magic left file or a magleft file, where instead of having for LVS, we actually extract the normal Bitcell because you can still extract it even though it has DRC errors. But then when we do DRC checking, we replace the Bitcell with a DRC passing cell that basically doesn't have the transistors. So all it has is kind of the top level metal, and that from not even the LI layer, so the local interconnect layer, but the metal 1 and metal 2, which passes DRC. So you're basically doing DRC on assuming that the Bitcell passes. And
Which you've already proven by looking at this
Well,
Skywater base rules and running the DRC when you generate the RAM.
so that Bitcell is actually given to us by Skywater.
Ah, okay, right.
So it is correct.
So they know it works.
So
Yeah.
they know it works. We actually can't change it. They won't, because they violate those rules. They've tested it during manufacturing, and they're like, this will work reliably. This is the memory cell. So you
It's
have to use
already fully optimized.
Yeah, you have to use the exact cell. You have to use the exact adjacent cells. It has to be exactly their usage. And so during MPW1, they actually came back to us at one point because there were a couple discrepancies where things were not quite as they expected it. And we iterated with them after the MPW1 tape out, or tape in, I guess. So before the tape out, and fixed some of those issues. They were relatively minor things, but.
Yeah. So now is it built into the OpenLANE that if it detects you're using OpenRAM, then it will automatically do this for you? Or do you have to make a configuration setting or?
That's actually something I've not followed up with the OpenLANE folks on. What it should do in OpenLANE is when you have a memory, either do DRC with just the left file of the whole memory. So don't even get inside of it to the decoders and stuff. Or actually, I think I gave Tim Edwards the maglef files for the cells. And so he was basically having it copy those over and use those instead. So I think that's what it ended up doing. But it's kind of the same methodology that I was doing in OpenRAM. Great. And for the single port, we hadn't set that up yet because no one was using single port except for us. And so.
Okay. Yeah. So for my course, I'm getting asked a lot with people who want to do designs that use memories. And I'm always saying, we just have to wait until OpenRAM is ready for us to use. And my plan for MPW3 is to take one of those 16 blocks that I use for people on the course and put an OpenRAM block in there, and then make that available to all the other individual projects so they can use it if they need to.
Yeah.
So it's really, I think it's great to have now a golden reference that we can point people to and say, this was taped out from MPW2. It includes a test, it includes instantiation, all the config is working, all the test is working, and everything is done. So I think that's a really fantastic resource for the community. I'm really happy that you made it happen, and also given the stress that I saw you all go through during MPW2, glad that I held off.
Yeah. I think some of the challenges specifically were things like the power routing. I think the power routing is kind of finicky in OpenLANE, where depending on
what you're saying, like the routing, because to start with, the pins weren't long enough, and then the router couldn't do. There's all these little bits that trip you up that you just take for granted, and then it doesn't work. So you have to figure out why not, and then how to fix that.
Yeah, and I think that's what took me an extra couple weeks and kind of pushed us to the deadline. Was just kind of iterating through those things where. We had used OpenRAM in commercial tools, and the commercial tools were a little more flexible in kind of what they expected for pin access and power supplies and things like that. And I think, we're still in kind of the early stages of the open source flows where they're a little more rigid in what they expect right now, but they'll improve over time, right? So
yeah, definitely, yeah. Okay, so we've had the kind of the context in the past, and we've had what's just happened from MPW2. So what's the plan for the future?
Yeah, so I think we're going to focus on performance for the next iteration as one of the main goals. We're also going to focus on, we're going to be for the, I guess there's 2 tape outs supposedly in the next year, one in kind of October and one December, I think are the rough deadlines. For the October one, our goal is to add asynchronous memories. We're working with Rajit Manohar from Yale, who's really famous in kind of the asynchronous computing area. And we're going to add it so that you can use a 4-phase handshake to talk to the memory. And it will basically be self-timed that way. Right now, we do a different way of doing the timing in OpenRAM. And so we're going to try to offer that option on some test, not for users, but as test runs, and get that done. And then we were actually at Skywater last week,
Yeah, I saw the
me and
photo. That
Tim
looks
Ansell
cool.
and so on. And we're hoping to get access to some resistive RAM devices. And so having non-volatile memory on the December run, that's what we're hoping to do. The idea is instead of that 6T Bitcell, we can use a resistive RAM device, which is essentially, it's kind of like a via between metal 1 and metal 2, but depending on kind of how much current you put through it, you can basically change the resistance of this device, and it doesn't change. If you cut power to it, it will remember. And so it's non-volatile.
Wow, I've
And
never even heard of that type of memory before.
yeah,
So it's a bit like Flash.
it's a bit like Flash, except it's a single kind of stack of metal, well, kind of with channels through it, and then the oxide molecules basically flow in and fill the channels or not to change the resistance. So it's one of the contenders to kind of replace Flash. It's also been used in a lot of kind of neuromorphic computing and machine learning kind of memories to remember the weights for different models. And I think this is exciting that we really want to do this because I think that could add kind of a new dimension besides just SRAMs to OpenRAM. So
Are there any plans for like on an FPGA, if you kind of say, okay, I need like 500 or 1,000 or 2,000, and it will try to fit it into the block RAMs that are available. Is there any plans for having it so that you could just say, okay, give me like a 500 length, 16-bit wide memory, and then it would instantiate an OpenRAM for you?
that's actually a really good point. That's been on my list. I have a grad student coming in that we're talking about exactly this. He submitted one of the designs. So this is Hadir Khan. He actually submitted to MPW1. He's from Pakistan. He's going to join my group. He did a chisel design for that, and like the back end of chisel kind of doesn't really map memories well. You'd kind of just have a mapping and so on. So we want to look at kind of how you infer memory devices from Verilog.
Yeah,
That's really
because if you
something that,
actually look at the way that if you read the logs that Yosis prints out when it's looking for like an applicable block RAM,
yeah.
you could have, okay, we've got the 1, 2, 4, 8, all these different varieties that have already been pre-made, simulated. You've got the behavioral models for, and then it can pick between them.
Yeah. So that's a great idea, and I definitely want to do this. I want people to help too, because yeah, changing Yosis is a game changer, right? Where previously you couldn't change the synthesis tool. I think we could even go one step further. There's this idea of having discrete memories that you can pick from, but there's also this idea if we can give it a range of memories and kind of a performance trade-off of that range, you can actually synthesize. Be like, I want to use two banks of memory from OpenRAM instead of one giant one because it's a little bigger, but it's better performance for my need. And so there's kind of trade-offs you can do, and even kind of the memory organization that we could do.
Yeah.
I don't know if that should be kind of its own interface to Yosis or what, but I think that's where a designer would usually come in and be like, okay, how do I want to make my cache? What size banks do I want? What size this? That I think that all can be automated. There's no reason it
Yeah.
shouldn't be.
Yeah. Awesome. Okay. Well, that is very great news, and I'm super looking forward
Actually,
to using OpenRAM in my next tape out. I think
actually,
that's going to be,
I should plug that I mentioned the cache because I have a
yeah.
student that I've been working with in Turkey that we're going to be releasing OpenCache. So you can basically say, I want a direct map cache, with this size tag and so on, and it'll generate the OpenRAM blocks for you, and then you can and the associated Verilog, and you can use it.
All the control stuff as well. It's easy to
Yeah,
get wrong.
yeah.
Yeah.
So
Great. And do you want to plug, is it WOSET? How do you pronounce it?
oh yeah, WOSET. So WOSET is the workshop on open source EDA technologies. So it says EDA. It's primarily EDA, but we also take some open source hardware designs. The key is open source. This is kind of the antithesis of most conferences where we require you to have an open source repository to get a paper in and to submit a paper. So yeah, it's a great workshop. It's been held twice in person. Last year it was virtual, and obviously growing pains going virtual the first year. It's going to be virtual again this November. It's associated with ICCAD, but we allow anyone to attend this workshop. since it's virtual and it's easy to pull off with a large number of attendees. And so there's 2 tracks of papers. You can either submit a 4-page paper and then we'll have a 15-minute video, or you can just submit like an abstract and then have like a 5 to 10-minute video. And any sort of project that we have a program committee that'll take a look at them and make sure that we have kind of good projects. And it's a great place to to show off your work. Because a lot of conferences, if it's open source, they say, oh, it's already out there. We don't want it in our conference. And so we take the opposite view of it has to be out there and we only want open source things.
Great. Okay. So, and if people want to apply, then I'll put the link in the video description so you can take a look there.
Yeah, great.
Awesome. Okay. Well, thanks very much, Matt, for your time. Really cool talking to you. I'm glad we finally got around to it. We've been planning this for at least 6 months now.
Yeah, too many deadlines. So
yeah. It was good we waited until MBW2. And I'll also post the link to the project application that you made that people can use as a reference for their own OpenRAM designs. And
we should work together on making a tutorial for using memories. I still want to do that. Just either generating memories from OpenRAM and using them, and also just using the memories from the library. I think both are useful.
Well, I think your reference is going to be great for that because it's got the tests with the behavioral models and it's got the instantiation and it passes all the eFabulous tests. So that will be a great starting point. But watch this space. We'll definitely improve the documentation over time.
Yeah, great.
All right. So thanks again for your time, and I'll see you when I see you.
Yeah, great. See you later.